All right, questions 3 and 4 from the Equations and Inequalities Step 2 booklet. And we'll do this one first, which is a nice little question about a triple simultaneous equation, followed by this one. So let's start with this one here. In the case A is 0, so okay, well, we take this, of course, and replace all the A's with zeros. Show that these have a solution if and only if B equals 11. So we did this in Timur, right? If and only if means, firstly, you check only if, and secondly, you check if. So firstly, only if B is 11 means that what we need to do is we need to find the solution to these and verify that the solution is B equals 11. So, okay, how do we do that? Well, why don't we just, take this equation, obviously remove the 0x because it doesn't matter, and then take this one, and I guess we could take these away from each other to get this, which means z is minus 2, and then we can put that into the second two equations. We could find y first, I guess. Y is minus 1 from there. And then we can put those two results into the third equation that we didn't use, and we'll get b is 11. So that shows that it's only if b is 11. What if b is 11 then? So now we need to start with if b equals 11. So we write them out with b as 11 there. And now we need to check that this actually has a solution as well. To do that, we can just add all three of these equations together to get this. And this definitely has a solution, right? Like it's just got a solution at z whatever you want, which then solves y to be whatever you want. And then once you have x and y, x obviously doesn't matter because they're all zeros. So you could also, I guess, make x whatever you want. But I think that's pretty much done. This should also be number 2, shouldn't it? Because I did that second. That should be number 1, and then that should be number 2. But anyway, next part is in the case A doesn't equal 0 and B equals 11. So we can write these out with B equals 11. Good. Show that these have a solution for Z equals lambda for any given number lambda. So, okay, let's solve these equations then. Let's times this one by 3 maybe to make the Z's match with this one and then take them away, I think is what I'll do to get this. And then maybe let's times this one by 5 so that we can take it away from this one and get the Z's to go away again and we get this. And now what you notice is if you double this one, because now we're working with these two equations because that's just a nice simultaneous equation in x and y. If you double this one, you actually get the same thing as this one. So therefore you would take them away, get 0 equals 0. So I think that just shows the solution for any x and any y. And therefore you could probably, I think maybe this is enough already. I went much deeper than this because it's helpful for the next part anyway. What I went on to say was, okay, let's rearrange that for x and we get this. And now the reason that's useful is because now I think I could make an equation for x, y, and z just in terms of one of them. And that's actually going to be helpful for the next bit. So I'm kind of skipping forward a little bit here, but I've got x is equal to this, and it's also going to be helpful to really argue this, I think, as much as I want. So x is equal to this. If I go back to the equations, I can put that value of x in there. All the a's cancel, which is absolutely lovely of them. So we get these three equations, which all simplify down to these three, which are very simple and very nice because they're all multiples of each other, right? Like this times by 3 is this, times by 5 is this. This is just one equation, right? So we just get this one equation that y equals 1 plus z. And so now I think I can write my x, y, z solution as this for x, this for y, and then z. And that's a solution. And also, if y is 1 plus z, I could even write that in terms of just z's alone, I guess an a as well, to get this here. And now I think this now tells me for sure that I can just pick whatever I want from that z at all, just anything. Because you pick a z, this becomes 1 plus z, that value, this becomes 4 plus 2 lots times that value divided by a. So this, I think, definitely shows me that I can just pick any z that I want. Here are some examples that I pointlessly did. But yeah, I think that's pretty much done now. I think I've gone maybe a bit overboard, but yeah. In the case a equals 2 and b equals 11, now notice, if a is 2 and b is 11, that's this case. This case that I went really far overboard to find, this thing here, works if a, for any value of a that's not 0, because of course of this division by 0 here that you get. So if a is 2, my solution works, right? The general solution that I found just completely works for this. So okay, well we can just put in a as 2, and we get this. And now we're trying to minimize x squared plus y squared plus z squared, but this is x, this is y, and this is z. So I can just make an equation entirely in terms of z. And I'm trying to minimize this plus this plus this now. That's essentially what this is asking. So how do we do that? Well, we'll just call it like g of z or f of z or anything you want. It's not going to matter. And you differentiate, of course. The minimum is going to be when the derivative is 0, and then when the second derivative is greater than 0, I guess. So okay, let's just derive it. We get this. All of these things can now just go together. You could have expanded this first, I guess, and then derived, but it doesn't really matter. This is equal to 0 when z is minus 1. And of course, g dashed of z is 6, which is always bigger than 0. So this is definitely a minimum point. So when z is -1, this here is a minimum. So then we just put in z as -1 into this original function. The answer becomes 1 minus 1, 1, 0 minus 1, I guess, when you put that in there. And then you could do these squares out together. You're obviously going to get find the solution. Oh, it's find for which it's the least. This is it. It doesn't actually ask us what the least value is. It's root 2, but it doesn't actually ask us for that. That's the solution for which it's got the least value. Anyway, the last part of this question, find a value for a for which there is a solution such that this is this and this is this. So, okay, I'm going to assume that that value is not a equals 0. And if I assume that it's not, I can just use the general solution that we had before, which has been very helpful to us thus far. So now I'm trying to minimize, or I'm trying to get this squared plus this squared to be less than 1, whilst getting this to be bigger than 10 to the power 6. That's the idea. So I need these two conditions to be met. Let's start with this one, expand the whole thing out and simplify, and we end up with this. This is, of course, just 1 plus 2z plus z squared, add z squared to get this. Take away 1 from both sides, factorize, or divide by 2 and factorize. We have solutions at z is 0, z is -1. So therefore, to be less than 0, we need to be in between those two roots. So we want z to be doing these two things. It just says find a value for a for which there is a solution that happens this. So let's just choose z to be -1/2 and put it in here, since that satisfies the first condition that we need. So let's just choose it to happen. If we put it in here, we get this, and then if we rearrange this, now notice a has to be positive here to make this work. So I'm allowed to times by a across here, and then maybe divide by 10 to the 6, because they're both positive numbers, and we'll get this idea instead. And of course, if I just pick a to be maybe 1 over 10 to the power 6, that's less than 3 over 10 to the power 6. So that will be a thing that will satisfy it. So I think that's an answer, and I think I'm pretty much done here with that question. The second question then is this thing here. So let's start with the first part. By considering positions of turning points, show that the curve has only one root, essentially. So okay, let's get the makings of a sketch going here. So for very large values of x, this is obviously very large. I mean, it's just a positive cubic, right? So it goes from here down to here. Y-intercept, what happens when x is 0, which just gives you this business down there. Q is positive, by the way, which means this is positive times by a negative means it's negative. So there, you could also just expand out and see that both signs are negative, and if Q is positive, then therefore that's obviously negative. Like I said, it's a cubic, so it just goes from there to there. And now, okay, so this is where we probably need to actually assess the turning points. Let's do dy by dx. There, or stationary points, I should really have said, probably. It doesn't really matter. Differentiate it, set it to 0. And yeah, we can, of course, solve that for x. It's going to be plus minus root q. But of course, well, it should be plus or minus root q, of course, I've written there. And yeah, what we'll do is we'll just ask ourselves, so okay, we know that there are stationary points therefore at root q, which might be over here somewhere, and minus root q, which might be here. But what really matters is, are they above the x-axis or below it? Because if they were above, that would, or below, that would change the shape of the graph. It might look like this. It might just kind of wobble like this, or other things as well. So let's put these root q's back into here to find the position of the graph itself. Now, this is q to the power half. Cubed is q to the power 3 over 2. And this is q to the power 1 times q to the power half, which is q to the power 3 over 2. The math is up there as well, I guess. So you get this, which simplifies to this. And again, if q is positive, then this number here is negative. And more than that, this thing here is just the y-intercept. So therefore, this is lower than the y-intercept. So it must be, and that was for root q, remember, so that must be down here somewhere, down there. So okay, now we need to assess minus root q. So we put that in. These minuses, the only thing that changes is these minuses make a plus, and that makes a minus at the front there. And then we can combine it together to make this. And this really matters whether this is positive or negative, right? Because if it were negative, this is the position, remember, of the stationary point at minus root q, which is over here somewhere. If it were negative, it would be down here, and the graph would look like this, and only have one root, which is what we were being asked to show. But if this is positive, so it would be up here somewhere, then it would be looking like this, and that has 3 roots. So I want to show this is negative. How do I do that? Well, there's probably a bunch of ways to do it. You could probably even do some more calculus, differentiate again, and so on. I just decided to if you factorize out q, you end up with something that's marvelously factorizable. It's just quite a neat little way of doing it, really. It's probably overboard. You could just differentiate and so on to find some minimum values or whatever. But looking at this value is always positive. And because q is positive, this is always negative. So this whole thing is always negative. So just quite a flashy way of doing that question. But in any case, we can now deduce that whole thing was negative always. So the graph looks like this, and only has one root, crosses the axis once only. So okay, good, so that's all done. Next part is, given that x satisfies this cubic equation, which I think is the same thing we were looking at before, it is, good, and that x equals this, they're asking us to make this substitution to obtain a quadratic in u cubed. So okay, let's make the substitution then. Let's just throw this straight in there to get this. This is a little bit annoying to expand, but it's just binomial, right? So just goes 1, 3, 3, 1. This is just turns out amazingly because some stuff cancels. It's really nice. You just end up with this. And if you times everything by u cubed here, you'll get this, which is totally a quadratic in u cubed, because it's u cubed squared to make u to the 6, and then u cubed, and then nothing over here. So that's all fantastic. So that's the quadratic in u cubed. To solve this, we could try and factorize if we really wanted to. Maybe it would work, but maybe it's just easier to get out the quadratic formula in terms of u cubed. So a is clearly 1, b is minus q into 1 plus q, and c is q cubed. So okay, we just put that all in there. And this is a bit of work, I guess. I haven't bothered to put this minus here because you're squaring it anyway, just in case you were wondering. And then this minus is just a minus b there anyway, so it goes away. So okay, we've got some work to do here. I can put the q into here before squaring it out, I guess, maybe, and then I could square it out like this, and then some stuff collects together. All of this term has a q squared in it, so I can factorize that out, and then I can root this and this separately, and of course the root of q squared is just q, so we end up with this here. But notice how this itself factorizes into a square, which will cancel with the square root, and you just end up with this here. And actually, when I sort of jokes about thinking about factorizing this, it totally would have factorized. Because if you actually follow this through, do the one with the plus and one with the minus, q plus q, and then q squared minus q squared, well, that's just 2q over q, so that just makes q. And over here, we end up with q minus q into q squared minus q squared, which is just 2q squared over 2 is just q squared. So this totally factorizes to u cubed minus q into u cubed minus q squared, which actually makes a lot of sense when you expand this out and notice it's just q minus q squared, so literally the sum of the two roots there and the product of them there. So I went a bit overboard there. There was much easier ways of getting that done if you had just spotted that, so well done if you did. But in any case, the answers will be u equals q to the third and u equals q to the 2/3 as our two things there. Of course, we need to put the x back. X is u plus q over u, so x is u, which is this, plus q over this. Q is q to the power 1, so that's q to the 2/3, and then here the same thing, which also happens to make the same thing. So therefore, it only has one real root, which is just this for values where q is bigger than 0 and not equal to 1. It was not equal to 1. Where did the not equal to 1 bit come into there? Was that important somewhere? Probably was important somewhere, right? Was it in the first bit? Was it? Oh, I don't remember. Where was that? Answers on the postcard. Write in the comments. I can't be bothered to find it where q is 1 was relevant. Anyway, we get this. Okay, what do we have now? If alpha and beta are, we've got a new quadratic equation, and we've got roots alpha and beta. I'm just writing this down because the golden rule of step is that you never forget things that you've done. You always keep them somewhere. So quadratic equation here has roots alpha and beta, which is this. So okay, well if this has roots alpha and beta, we can write it as t minus alpha, t minus beta, and then we could expand this out and we could just compare some coefficients to find q and p in terms of alpha and beta. So that's exactly what I did. I just compared some coefficients of the t's and of the non-t's, and we get this, which is fine. And now, if you've done A-level further maths, which I'm imagining most of you have done, you'll have studied how to, do the combinations of roots and things like that. I'm kind of just assuming you haven't. I'm going to do it from scratch, just because it's possible that you haven't. So a cubed plus b cubed. And this is also a really nice little thing that you don't need to use in this question, like I just said, but is well worth bearing in mind. The sum of cubes is factorizable, because if b was minus a here, this would become 0. So by factor theorem, alpha equals minus beta as a solution, so therefore alpha plus beta must be a factor. And then you can just do some division or just do some spotting of terms to notice that this must be the thing you get to make this overall, because you get with alpha cubed, you get beta cubed, and then this term here cancels with this term here, and likewise with the other bits. So you end up with this here. Now, how is that helpful? Well, alpha beta plus beta is just p, and alpha beta is just q. And if we write the beta squared in front here, we get alpha squared plus beta squared, which looks a lot like p, and it basically is p. It's p squared, right? It's p squared minus the extra 2 cross terms that you get. And now this is me just being super extra, But if you do it in black pen, red pen style and just add a 2 alpha beta just to take them away, this is alpha plus beta all squared, which is p squared, and this is just minus 2q, which will make minus 3q in total. So you end up with p into p squared minus 3q, which is this here. And yeah, this is just me reverse engineering that, but I think most of you will be more familiar with that idea, and you'll end up with this in total. So that's the relationship between, that's a relationship, I guess. I know, what have I even done here? I've done the first bit here. Now we're here. It's given that one of these roots is a square of the other. So either alpha squared equals beta or beta squared equals alpha. It probably doesn't matter a huge amount. Now, considering this thing here, now if alpha squared equals beta, this is 0 because it's 0 times something. And if beta squared equals alpha, guess what? This is still 0 because it's this times 0. So they're 0 either way. However, we could also expand the whole thing out anyway, just for fun. We could expand out the whole thing because this is alpha beta all squared. This is alpha beta, which is just q. And this is minus alpha cubed plus beta cubed, which I believe we just found was this thing here. So let's put that in and we get this, which I guess equals 0 because of what we just said. And now our objective here is to determine the value of p in terms of q. So we take this equation, which equals 0 because, of course, we argued that it did. We take this equation and we're supposed to try and rearrange that for p, which is supposed to find p equals in terms of q. And you might be sitting here wondering, how on earth are you going to do that? That's super complicated. What? It's a cubic. How? What? How am I supposed to figure out that? Until you remember the golden rule of step, which is you never forget anything that you've done in a step question. Look at this. Factorize out the q. Does it look familiar yet? It should do, because it's exactly this, with p just replacing the x. So therefore, the solutions to this must be p equals q to the 2/3 plus q to the 1/3. Never forget anything you do in a step question.